Hi, welcome to a special part 5 of chapter 7, which really isn't in your textbook, but is on the AP exam, where we talk about the photoelectron spectroscopy, or PES for short. So what is it? How does it work? Well, you take your sample and you expose it to some electromagnetic radiation. It could be X-rays or high energy light. And then you analyze the electrons that jump out of the sample. And you get data that kind of looks like this, where plotted on your y-axis is your number of electrons that were collected. And on your x-axis, sometimes they'll say this delta UE, or they'll call it binding energy, or for our purposes, we're going to call it ionization energy. Most of the time, it's in megajoules per mole. So we're not talking about one atom here. We're talking about a mole of atoms. And you will get some peaks. Now, this is for lithium, okay? And you'll see that the electrons that are generally closer to the nucleus will give you a peak that is on the left. But I want you to look at the scale of your x-axis and notice that it goes from low ionization energy to high ionization energy. So kind of think of your nucleus. If you were drawing your atom, think of your nucleus here. And the electrons that are closer to the nucleus are going to need a higher ionization energy to remove them because they feel a greater force of attraction. The ones that are further away will need a lower ionization energy. So electrons generally further away from the nucleus are more to the right at a lower ionization energy. Each peak represents an electron in a sublevel of the atom. The bigger the peak, the more electrons. So we know lithium's electron configuration is 1s2 to s1. The 1s2 electrons are closer to the nucleus. So this peak here would represent the 1s2. And this peak here would represent the 2s1. Now notice this peak is twice as high as this peak because there are 2 electrons in here and there's only 1 electron in here. So let's look at hydrogen versus helium. So hydrogen, you know, has an electron configuration of 1s1 and helium is 1s2. Again, notice high ionization energies to the left, low ionization energies to the right. Hydrogen has 1 peak because it has only 1 sublevel and it has 1 electron in that, so that kind of makes sense. Now I want you to look at helium's. Helium has 1 peak and it's twice as high. So here you have 1 electron. It is twice as high because you have 2 electrons in helium. But why is this peak of helium closer to the nucleus? Notice this is at a higher ionization energy, 2.37, where this is at 1.31. Remember your nucleus. Envision it here. So helium's electrons are closer to the nucleus. And that is because your effective nuclear charge is higher in helium. So it makes sense that the ionization energy for helium is higher than the ionization energy of hydrogen. So if you look down here, it kind of sums it up. The helium peak is twice as tall because there are twice as many electrons in the 1s sublevel. The helium peak is also further to the left at higher energy. So you need more energy to remove the helium electrons. And this is because they are held more tightly, because they have a higher effective nuclear charge. Remember, helium has 2 protons, where hydrogen only has 1. So you can learn stuff from the height, how many electrons are in that sublevel, and the location on the X, what is its ionization energy. So if we compare lithium and beryllium, remember lithium is 1s2, 2s1, and beryllium is 1s2, 2s2. So they both have two sublevels. So you would expect 2 peaks for each of them. And that's what you see here. Lithium is in the blue, and beryllium is the pink. So using the electron configuration and the graph, explain the heights and locations of the peak for lithium and beryllium. So look at lithium's peak. The first one is higher than the second one. Why is that? Well, look at your electron configuration. The first sublevel has 2 electrons in it, but the second one only has 1. In beryllium, both peaks are the same height because both sublevels have 2 electrons in it. But notice beryllium's peak have shifted to the higher ionization energy. Remember, this is higher ionization energy. And that is because of the effective nuclear charge. Lithium has 3 protons. Beryllium has 4. So because of the higher Z effective, beryllium's peaks shift left. They get closer to the nucleus. So if we look at neon here, neon has 1, 2, 3 sublevels. So it should have 3 peaks. And your 1s will be here, 1s2, your 2s2, and your 2p6. So this is kind of how they verified that the s holds 2 electrons and the p can hold up to 6 by looking at these PES peaks, okay? So you see that this is much higher than the other two because there's more electrons in there. If we look at scandium, scandium has a D sublevel. So there are 1, 2, 3, 4, 5, 6. Oops, 1, 2, 3, 4, 5, 6, 7 sublevels. So you should have 7 peaks. The closest one is always your 1s2, and your 2s2, and your 2p6, and your 3s2, and your 3p6. Then notice the 3d1 is written before the 4s2. Because the 4s2 is further away from the nucleus, those electrons have lower ionization energy. So if you are going to lose an electron, the 4s will lose electrons easier than the 3d, and that's what we noticed when we were forming our ions, right? So notice it takes more energy to remove an electron from 3d than 4s. This is because as electrons are added to the 3d, they shield. So as you're adding electrons here, they're shielding the 4s from the force of the nucleus. So it makes it easier to remove an electron from the 4s than the 3d. So remember, when transition metals make positive ions, they always take from the s electrons first. And this technique kind of proves that. And that is the end of our tutorial on PES.